good lunch, Christian.
Hey, what's up, Mike?
Christian, I don't even want to know what you're going to do with that pickaxe and why you have it in my office.
Well, first off, it's a Matic. Get that straight. And secondly, I'm getting ready for the zombie apocalypse, if that wasn't clearly obvious.
Okay, Matic, pickaxe, whatever. But zombie apocalypse? That's the dumbest thing I've ever heard. Why?
Have you seen this article? There's 7 billion people on this planet. The population's growing out of control. Someday, this is just like the movies, someday someone's going to do some crazy experiment with a monkey and we're going to get this virus that kills most of the population and causes them to turn into the walking undead. And I tell you what, I'm not going to be caught unprepared.
Is that why you have this sledgehammer in my office too?
Of course, you always have to have a second weapon. You never know. What if you drop this one?
Okay, look, here's the deal. You've been watching too much Walking Dead. This is not how population growth happens. I get that the human population is exploding. I saw the same article. It's interesting. But human population growth is a complicated thing, just like any population. It doesn't grow forever.
What do you mean?
Well, what I mean is before we have a zombie apocalypse or whatever else you worry about, a bunch of other things are going to regulate the population.
Such as?
Tell you what, let's take a few minutes away from sharpening your little pickaxe here, and let's take a few minutes from sharpening a little Matic, and let's go talk about population growth.
So do I have to go to that place again?
Make a deal, you can bring your pickaxe.
I can bring my Matic?
Yep, that too.
Perfect.
All right.
Back again, huh?
Here we are. Listen, let's just talk through this population growth problem before you do something rash with this weapon.
I think I'm being very rational.
Now listen, I get that the population's growing. I mean, it's pretty scary. I saw the same article in National Geographic. And
right.
I thought it was great. But, you know, populations don't grow forever, and neither is the human population going to grow forever.
Wait, what do you mean?
Well, I mean, have a look at the history of human population growth. If we reconstruct that history from historical records and then also census data from modern times, you do get the impression that something crazy is going on. You know, it's going along, chugging along, and all of a sudden, boom, it takes off.
Take a look. It skyrockets. I'm telling you, this is what's going to happen.
I get it. I know, and it looks scary, but when you think about what's going to happen 100 years from now, you're extrapolating from what happened in the past to what's going to happen in the future. And that's not necessarily a good thing to do.
Why is that?
Well, I mean, let's think about the model that you have in your head when you're doing that. So you might have a simple model like this, that the change in the population size or the population growth, let's say from one year to the next, it's going to be a function of how many people there are now that are reproducing and dying and the rates at which they reproduce and die, right?
Right.
Now, we can call those rates at which they reproduce and die, the birth rates, the death rates, we can call that the per capita growth rate of the population. That's what a biologist would call it. Do you know why?
Does it have something to do with, well, I hear about per capita with economics. Does that have something to do with dollar bills, maybe money, or Washington, D.C. or capital?
No, nothing to do with that stuff. Well, in a very direct sense. Just indirectly in the sense that they all have something to do with the Latin word capita, which is head. So you have a head, I have a head, each
Zombies
person has
won't
a
have
head.
a head.
Zombies, sometimes they have a head.
Not after I'm done with them.
There you go. But if you count the number of people, it's like counting the number of heads in the population. So per capita growth rate means the growth rate per person. So naturally, if you get the chance that a person is going to give birth and the chance that a person is going to die, you can use that to figure out the per capita growth rate. Now, what a biologist would do is take those rates, the birth rate, might call it little b, and the death rate, they might call it little d.
All right.
Makes sense, right?
Right.
You got to
Makes
pick a
sense.
letter. And if you subtract the two from each other, you get that per capita growth rate. So if the births exceed the deaths, that is b is larger than d, the population will grow, right?
Makes sense.
That per capita growth rate is positive.
Right.
And we're going to actually call that per capita growth rate little r. That's what your textbook calls it.
Oh, yeah, that's right. I think I remember that. Okay, yeah.
Now,
Makes
if
sense.
you're going to use a value of little r, what are you assuming about that population and the births and death rates? If you use the same value of r year after year after year, what do you assume about those birth rates and death rates?
So you're saying r is essentially has to deal with birth rates and death rates. So if r doesn't
it's
change,
birth rates minus death rates.
right? So if R doesn't change, then I'm guessing those values don't change.
That's right. So you're assuming when you use this kind of model, the birth rates and death rates, they just don't change, no matter how much the population grows.
Finally got a question right. Okay.
Yeah, there you go. Now, what happens when you make that assumption? Well, you get this exploding population growth, right?
Right, the population growth I'm worried about, and we all should be worried about.
Right. Well, that's called exponential population growth. And you can see here two examples.
Okay.
One for a fairly large value of R, which is equal to 1, means the birth rates are much higher than the death rates. One for a smaller value of R, where the birth rates are still higher than death rates, but it's not as high.
Okay.
You can see that in the large value of R, it really takes off very much like the human population growth has taken off.
Right. Okay, that makes sense.
Now, here's the kicker. Birth rates and death rates don't stay the same. So this model is a really bad example of what might happen, way out in the future.
What do you
It might
mean?
be good for the short term, but once those birth and death rates change, that model's not going to work.
Hold on. I need an example. What are you talking about here?
Okay, well, let's think about it like this. What if I were to do an experiment like the one that had been done by Gauss about 1930s, I think he did this work. Now, Gauss was a student in Russia doing this research, and incidentally, he couldn't even get into grad school with this stuff.
Right, he was an undergrad when he did this, right?
Yeah,
Okay.
he couldn't even get a position in a lab in the U.S. I bet they're kicking themselves now.
I probably would be.
Yeah, he's in every textbook I've ever
Right.
opened. So if you look at what he did a very simple experiment. He took a population of single-celled organisms, paramecium. He put those paramecia cells into a flask with a set amount of resources.
Okay.
Then he let them go. Let them
Makes
do their
sense.
thing. They reproduced. They died. More of them reproduced and died because the population grew. And in fact, at first you see this population, this population takes off like crazy.
Right.
It shoots way up.
Which is what we're seeing in another graph, right?
But look what happens next. After a few days, the population then starts to bounce around, leveling off, and then the population crashes.
Wait, so why did that leveling occur in the population crash? What was that dealing with?
Well, what do you think's going on there when the population starts to level and then crash?
Well, so it gets really high, maybe something about birth rates and death rates changing. Is it maybe the resources are running out or something like that?
Yeah.
Okay.
It could be one thing that the resources are running out. It could also be all the waste that they produce are accumulating.
Okay.
Some of those are toxic. So a bunch of things are going on here which make the birth rate go down and the death rate go up. And when those two things come together, the population stops growing.
Right, okay.
When the death rate exceeds the birth rate, the population crashes.
Population goes down.
Right?
Okay.
Now, you want to know how we can put that information into a model?
Sure, let's see how it works.
Okay. So we could take that model before, which looks like this,
Okay.
and change it. Before we said that value of little r, the birth rate minus the death rate, that stays the same, no matter how much the population grows.
Sure.
So it's a flat line,
Sure.
right? But now we want that value to go down as the population grows, because presumably births go down and deaths go up.
Right.
Okay. When things get more crowded.
Right.
So we can just make a straight line.
Okay.
Right? So as the population grows, that value of little r goes down as a straight line. In fact, if you want to see how we can turn this straight line into a model that's in your textbook, watch my other video where I go through the math. It's nothing but algebra.
Okay.
Nothing to be scared of.
All right, well, math is terrifying, but I know it's important in biology.
I'd take a look at it.
All
It
right.
makes things a lot easier to understand. When that population stops growing, that is when the r goes down to 0, we can call that a special thing, and that's usually the carrying capacity.
I've heard this term, and I've seen it in a textbook a lot. Okay.
Yeah, the idea is that's the size of the population that the environment can handle. Anything more than that, and it exceeds the resources that are available.
So I'm a little confused. Can you take, this is a little bit different than the other figure. Can you sort of show me how this figure goes in with Gauss's work?
Yeah, so if we take this back to Gauss's work, we can understand what's going on here. So early on, we have initially an exponential sort of growth, this sort of like really rapid explosion, but later on it starts to slow down. And that's the kind of growth pattern that you get with this model that we just came up with.
Oh, so that flat part's basically where we go to the 0.
That's
basically.
right. So right here,
Oh,
this
okay.
flat part's where the birth rate equals the death rate.
Right.
Right? And if we wanted to, like Gauss did, we could estimate what that carrying capacity is. And he thought from his data that it's about 145 cells per
okay.
half a cc.
Okay. So, and then the population crashes. That's just because deaths are
he
exceeding
never added
birth
any
rates,
resources,
right?
so sooner or later they all ran out.
Okay.
And then the population crashed.
So, so it sounds like the zombie apocalypse isn't going to happen, but aren't human populations still going to grow, at a really fast rate? Is there any way we can
They are growing, yeah.
control that?
Scary. I've been thinking about this, Christian. I think what we need to do is market some bumper stickers, something like "Save the planet, kill yourself," right? Then everyone else works on the death rate while we work on the birth rate. Not together, though.
Not together. I think I'll let you do that.
All right, well, anyway, at least you know something about population growth rate, and you know that the human population isn't going to grow until it explodes into some kind of zombie apocalypse.
So I probably don't need this. The zombie apocalypse isn't going to happen, right? So there's no need to be prepared?
Well, let's not get carried away. Even I'm prepared for a zombie apocalypse.
Oh, nice.